Welcome back. We're going to look at key points for quadratic graphs today, and I spent a bit of time trying to find a beautiful background for you, and I think I found the best one that PowerPoint has to offer, so I'll give you 2 seconds to marvel at this. That's your 2 seconds. Okay. Recap from last lesson. So these are the 4 points you had to send in, kind of saying what these look like, and it was difficult to describe them in words, and it was difficult for myself to offer feedback. So I thought I'd put this in and just spend 2 minutes on this for the people that I possibly didn't get back to or didn't express my words in the best manner. One thing to note about all of these, which SpongeBob's teaching us nicely in the corner, is that we aren't talking about that triangle, we aren't talking about square, we are talking about curved lines. If you're ever drawing anything that is a quadratic, a cubic, a reciprocal, anything that isn't a straight line, it needs to be done curved. No dot to dot. Nice curve, the best you can do. Nice curve. And if you know where that scene's from, I'll give you a commendation. Message me if you know where it's from. From my experience of working in schools, is people your age never watched SpongeBob, and it's very sad to think about. Don't get distracted by that for the rest of me speaking though. So positive quadratic, that is this. It's a U shape or a smiley shape. Very smiley. And that's where we've got something where it's y equals x squared, where this is a positive. It could also be 2x squared, and you can have anything at the end as long as it's just x's or numbers. So you could have minus 2x plus 3 plus 12x minus 4.1, I don't know. You can have all sorts. As long as x squared is there and it's your highest power. It could just be x squared on its own. I mean, that's just the x squared graph. Negative quadratic, that is an N shape or a frown shape. So a sad quadratic. He's being negative today. And that is that one here. That is where we've got an equation where it's y equals minus x squared, so you can see that we've got that there. And then whatever comes after that will dictate kind of whereabouts it is and how long it is and how wide or short or fat or slim and tall. But literally, if you've got a minus x squared, it's going to look like an N or a frown shape, and that could be minus 2x squared again, or minus any lots of x squared. A cubic, well, when this is positive, it's going to go up, down, and up. And this is something that's got an x cubed at the front. It could be 2x cubed, it could be 3x cubed, and it could have anything afterwards as long as the cube is the highest power. So you can have some x squareds in there, you can have some x's, some numbers. If we expand this over here, we'd get something like y equals x cubed plus, what would that get us? 0 lots of x squared. I don't know. I can't do it in my head. But you can see that goes up, down, up. We can also have them where they just kind of go flat and up, but you can see it's still following the same pattern of going up, stopping or going down, and then going up. And if it's negative, it's just going to do the opposite. So instead of up, down, up, it's going to go down, up, down. Or it's going to go down, flat, down. And that's where we've got where it's minus x cubed and then some stuff afterwards. And then reciprocal, and I forgot to say that that one is that one. And reciprocal is our last one. Reciprocal is where we're going to have something where it looks like y equals 1 over x. So x is on the bottom, and you might know from your Powers laws that it means that, but you'd never actually see it in that form. You'd always want to write it in the fractional form because it's what people recognize. This would be a positive one, so when it's in these two quadrants, it's positive. And you'll have got from when you were plotting your points that it never actually touches the axes when it's just the y equal 1 over x or 2 over x or something like that. Never actually touches these. Because when you think about dividing by 1 divided by a number, if you divide 1 by a really big number, you're just going to get a small decimal like 0.00001, something like that, but never 0. and if you divide it by a really small number, you're just going to get closer to, well, you're going to go into your thousands, your 10,000s, your millions, etc. You'll get close to infinity, so somewhere all the way up here. But you're never actually going to get to 0. And what we call these dotted lines I've drawn, which are in this case are the axes, we call these asymptotes. And I've fact-checked my spelling just before this video, and it does have that P in there. It's a bit weird. It's a weird one to spell. But asymptotes, and that basically means it's a bit of a line where it gets infinitesimally, which means very, very, very close to, but never actually touches it. And the graph kind of comes down here, down, 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 and then it just reappears back up there. And just think about it with your substitutions. If you've got minus 0.001 going in, you're going to get minus a million or something daft like that. And then as soon as you change it to a positive number, you're going to get large values again, but positive, so they'll be all the way up there. And if we have a negative reciprocal, it's actually just going to look like this. So negative would just change what quadrants it's in. Okay, so actually on to the key points of quadratics today. I'm going to show you, I'll discard that. I'm going to show you something I have made. Just a quick explanation of this, then I'm going to go on to my Google tab and I'm going to show you the one that you can be playing around with, because I've had to export it onto the GeoGebra website, not on the actual creation tool. But what I've got here is the some sliders. So what this does is, if you keep an eye on this equation of a quadratic, the a is going to change the number of the x squared. You'll probably just want it as 1, but you can see if I change it to that, it goes to 0, and if I change it to 0, it just turns into a straight line because we've got no x squareds. Changing your b, that's going to change the number by the x. Let me leave that at 2. And then if I change the c, that changes the number at the end, and you can see that that is still just the y-intercept, this number on the end. So 4, 4, 5, 5, 6, 6. So the rules we know about lines and graphs still follow, where the y-intercept is just the number with no x's by it. Because if you make x equals 0, these will still disappear. And that's the case for all graphs. So if you tick these boxes, you can see that that's making some coordinates and some dots appear. These are called the roots. So the roots are where the graph crosses the x-axis. And roots are actually the solutions to the graph. If you went to solve this quadratic, which is what we're going to look at when we go on to some questions, finding the roots, or finding where it crosses the x-axis, is actually finding the solutions of x that solve this equation. And if you put, let's say we put 1 into here, we got 1 squared is 1 plus 2 lots of 1, that makes 3, and then take away 3, that gives us 0. And when we solve this, when you solve a quadratic, you always want to make y 0. So if we were to solve this, I would say 0 equals x squared plus 2x minus 3. And then I would go ahead and solve it, which you'll learn properly in another lesson soon. But the reason why we make it equal 0 is because the solutions are on the x-axis. And then the final bit of this is the turning point, and the turning point probably is something you could have figured out for yourself, but it's where the graph goes from, instead of going downhill, it turns around and it goes back uphill. And if we make this a negative graph, instead of going uphill, it turns around and it goes downhill. So it's that coordinate where either it's its lowest point or its highest point. Sometimes you might hear it as minimum and maximum point. Maximum point would be on a negative because it's the highest point here, and the minimum point would be the lowest point here also. So turning point, minimum point, maximum point, they're all the same thing. So if we have a quick look at the factorized form, actually. So what I've done here is, this is a quadratic. This is the quadratic. If you factorized it, you can double check that it's right. And just have a look at the numbers and have a look at the roots. I'll slide it a little bit just so you can see the takeaway sign a little bit there. But we've got x minus 1, and then we've got a root of 1, 0. And then we've got x minus 3, and then we've got a root of x plus 3, and then we've got a root of minus 3. Not going to go into too much detail of that because that's another lesson next week, but just to think about that, and as I move these, and as you play around with it, just follow that and see see what you spot a pattern. This could just be a coincidence. So two solutions to this is very common, because if you think about when you square root something, if you square root 9, you could have minus 3 or you could have 3, because minus 3 squared is 9 and 3 squared is 9. So it makes sense that with a quadratic, which is an x squared graph, we could have two solutions going. If I change this a little bit, so I'm going to go for x squared plus 6x plus 9. What do we notice about this one? So we may notice that when we factorize it, we've got two of the same brackets. And when I check my roots, which is where it crosses the x-axis, I have the same coordinate twice. So in this case, we have what we call a repeated root, where we seem to still have two roots, but it's just the same root twice. And then when you write out your answer, you would just write it once, because you don't need to write it twice. And in this case, the turning point would be the same, because it's the lowest point. But it's very possible, if you can factorize something and it's the same bracket twice, we could write that as x plus 3 squared, couldn't we? X plus 3 all squared, instead of x plus 3. That would result in us having just one solution. And then if I change this just a little bit, we can see we've got question marks, and it doesn't seem to want to factorize it. So I know my class have seen some quadratics where we've looked at factorizing and you've claimed to me you couldn't factorize it. Well, this is the case, because if you drew it, it would never actually cross the x-axis. And we can't have roots, and we can't factorize it if it doesn't cross this x-axis, because they are the solutions, and they are what help us figure out what goes in our factorization. Not that we've looked at it that way, we've looked at it a different way, but you could also look at it this way. So it's very possible for something to have no roots, and that is just if it's floating above, or if we had a negative one and it was floating below. So again, that would have no roots. Okay, I'm going to go on to the one you are going to look at, and I'm just going to show you that it works pretty much the exact same. I've done all my explanations on this, I didn't plan to, but I'm just going to show you what yours will look like. So I'm just going to go on to my internet tab. Oh, meant to close that tab. That was a joke, by the way. Did you laugh? I hope you did. Smash like if you laughed. So this is exactly the same. I would use this on a laptop, PC, or a tablet. It doesn't work very well on a phone. But you can see the factorized form changes. You can turn this on and off. Have a play around with it. The questions you answer, why don't you try and recreate them in this? It's pretty easy to just slide this about and recreate what the quadratic is, and you can just double check your thoughts on this, or you can just have a play around and try and learn some stuff about quadratics. So there we go. And I'm going to do two quick examples which are a bit more specific to kind of the questions you will be answering. So, find my pen. We've got a graph here, and we're going to find the roots, which is this what we call solving, of a quadratic graphically. So if we want to solve 2x squared minus 3x minus 2 equals 0, we'll notice that these are actually the same. So we're really solving where y equals to 0. Y equals to 0 on the x-axis. So we're actually just spotting these two coordinates here. That's going to be minus 0.50, and this is going to be 20. So our solutions are going to be x equals minus 0.5 and x equals 2. And I'd always just write it out like this in the question. I'd write solutions and then write your two values of x equals. We don't need to put 20 or anything, because we just want to know the value of x. And if we were to find our turning point, we've not been asked, but the turning point is just going to be this coordinate here, isn't it? And that is going to be 0.8 minus 3.2. Okay. And then what if this doesn't equal to 0? Which is what we've got here, equals 2. Again, this is y. This is the same thing, y. So y equals 2 is basically what this is saying to us. So I'm going to plot the line y equals 2 because this is an equals 2. So if I plot the y equals 2, remember that's a horizontal line, a line where all the coordinates have y equals 2. So 0, 2, 1, 2, 2, 2, 3, 2, etc. This is the line y equals 2. We're basically wanting to know where the graph y equals x squared plus 2x minus 1 is the same as the graph y equals 2. And that is where they cross each other. So here and here. Well, let's have a look at these points. It's going to be minus 3, 2. And it's going to be 1, 2. So again, just write out solutions. X equals minus 3, x equals 1. We don't care that it's y equals 2 because we've got that written in the question and there's no y's in here. We only care about the x values. So that is it. There'll be some questions for you to have a go at. Hopefully that is helpful. Have a play around on the GeoGebra file if you wish. I think it's quite good fun to play around with them sliders. Yeah, and that's it. Cheers.